so I'll try to keep it as interesting as possible. So I'll start with, before we get to what's partitioning, I'll just do a quick refresher of the DAG if you haven't seen this picture 10 times already. So in Apex, when you're building your application, right, you write operators and you connect them with the DAG and then you launch it, right? So simple. However, big data is not that simple, so you have all your operators, but if you just run them as a single instance or a single process, you may not be able to process all the data that's coming in, right, and have the desired SLA. So you typically need more than one instance of your logic running and simultaneously processing the incoming data. So that's where partitioning comes in. So in this case, I will illustrate first some of the partitioning concepts, taking simple DAGs. So let's start with a concept of a unifier, right? So let's say you have an application with three logical operators, in this case, 0, 1, and 2. Now, you have, let's say, for your given data rate or a given data stream, you need to actually to basically process it with a certain latency and throughput. You may actually need to have more than one partition of the logical operator 1, right? So logical operator 0 may be just an input operator that's fetching data from somewhere, so it's may not be doing a lot of work. So it could remain one instance, but the next operator you may be doing some heavy parsing or whatever. So to keep up with the data rate that's coming from the first operator, you need to actually have more than one instance. So this is where your operator 1 gets partitioned into multiple instances, and the data that's coming out of stage 0 gets actually split, and each of these instances of 1 will basically receive subsets of the data. So when this happens, now effectively what was a single process is now divided into multiple processes. So each of these are now working with subsets of the data, so their results may need to be aggregated before it goes to the next stage of processing, right? So let's say if you're computing something like an average, now you have partial averages across these individual partitions, you need to combine them to get the final average. So unifier is actually just another operator, but an operator developer can specify the unifier logic. So the unifier logic may would most probably depend on the logic of the operator, right? So if your operator is doing an average, you may actually want to send an average and a count downstream so that the unifier actually takes the intermediate averages and counts and compute the final average, right? So the unifier logic will be dependent on what the operator is doing. So the person who's actually writing the operator number 1 can also provide the logic for the unifier, and it will run as another operator, right? So the person who's writing operator number 2 doesn't have to worry about aggregating those. The contract by operator number 1 will be complete. So that's the basic notion of a unifier. So now let's extend that if you have multiple stages that are partitioned. So in the next DAG, you actually have 4 operators. Now stage 1 is partition and stage 2 is also partition. Now you don't need to have the same number of partitions for every stage. So each partition can be scaled independently based on the kind of complexity of processing it's doing. So stage 2 probably is doing lighter processing in this case, and 2 partitions is sufficient. Now, if we extend the unifier paradigm to this one, we could actually bring all the data to a single unifier and then split it up again, but that will actually cause a bottleneck, right? And typically, with big data, you always find a way to partition or segregate data. Usually it's key-based or something like that. So in this case, a much better approach is actually to use separate unifiers, and each unifier is only taking the subset of the data that is intended for the downstream, right? So in this case, you have 2 unifiers, and both of them are basically getting, let's say, if it's all uniformly distributed, let's say half the data, and thereby you're avoiding the bottleneck that you would have in case of a single unifier. So this is what we call N by M or M by N partitioning. Now, if you wanted to go back and have a single unifier, that's an option that's available as well. So some more partitioning mechanisms. So let's say you have, you're doing an ETL app, you have data coming in, each tuple you're just processing independently, you want to perform a series of operations. You may want to perform some, let's say, filtering, enrichment, and something else. And you're just working with each piece of data independently, and there is no need for you to actually shuffle the data across. In this case, you can have the same number of partitions for successive stages, and then without any shuffling, right? So in this case, stages 1, 2, and 3 have 2 partitions each, and the data from one partition of 1 will basically go to the next, the corresponding partition of 2. Like 1A goes to 2A. There's no data from 1A to 2B, right? So that's parallel partition. So, and you can have combination of this in your DAG. So you can have, a couple of operators in parallel partition and a couple of operators in M by N. So you can have mix and match. And the last one is Cascade Unification. So suppose you create a large number of partitions, and the results, you need to basically aggregate the results before you get the final output. Now, bringing them all to a single unifier may not work because you have a lot of data, right? So you may need to actually unify itself in stages, right? So maybe a unifier can handle 2 partitions or maybe 5 partitions. And now if you have 25 partitions, right, then the platform's smart enough to create multiple stages. In the first stage, it'll put 5 unifiers, and the second stage, it'll put 1 of them. So that's what this picture is showing. So in this case, we said a unifier can only handle 2 partitions. So the platform automatically inserted 2 stages of unifiers. In the first stage, you have 2 unifiers, each reading from the 2 partitions. And the next stage, you have 1 unifier that's taking the result from the 2 unifiers. Now, if this were 8, this would become 3 stages, right? So that's automatically inserted. So, and then another unique feature that's to Apex is dynamic partitioning. So what's dynamic partitioning? It's essentially changing partitioning while an application is running, right? It actually also includes the ability to dynamically determine the number of partitions to begin with, right? So it includes both of them. But more useful is when actually you can change partitioning at runtime. So what are some of the examples? Maybe you are processing 1,000 events per second, and later in the day, that increased to 10,000 events per second or 100,000 events per second. Now, to meet the same SLA, essentially to process the data with the same latency, right, you actually need more partitions, right? So, and you don't want to you don't want to basically commit all your resources at the beginning of the application when the amount of data is low, right? Instead, you want that application to elastically grow and to actually stretch and again come back to its to a smaller state, contract when the stream is when the data rate goes down. So the dynamic scalability provides that, and we have some interesting examples here. So our input operators also elastically scale. So if you look at the Kafka operator, basically it creates number of partitions based on number of partitions on the Kafka side. So so essentially this is a fairly useful thing to have. So I'll basically illustrate the next topic. I'll go into some of the describe some of the partitioning with the help of an example. Let's say you have a sample application that's reading from Kafka or any other message bus and then writing to database. So you may be reading from the message stream, doing some parsing, filtering. Parsing actually is breaking the lines into words. You're dropping some words, and then you're counting how many times each word occurs, and then finally writing to a database, right? So when you want to build this application, you basically write some code like this. You create all the operators, and then you connect them up, right? So how would you specify partitioning? It's actually very simple in most cases. So here, for example, I'm specifying, so the Kafka operator I told you is dynamically scaled, right? So you don't need to specify any partitioning there. The parser, you can specify how many partitions you want. So here I'm basically picking a fixed, static partitioner, which is called a stateless partitioner. And I'm saying start with 4 partitions. So it's going to be fixed, and it's going to remain at 4. And then I'm saying that the counter is going to be parallel partitioned, right, to the parser. So if you look at the output, you can see that the same DAG that you created here, right, with these, the input, parser, filter, counter, and output, when you're actually at runtime, is going to look like this. So there are two inputs because there are two partitions for the topic on the Kafka side. So two partitions dynamically got created for the input operator. We specified that the parser has 4 partitions. So we have four parser partitions, and it's m by n, right? Because Kafka had 2 and parser has 4. So the 4 unifiers got inserted. Then we said filter and counter are parallel partitions. So 4 partitions got created for filter and counter. And finally, for the output, we didn't specify any partitioning. So all the results of those 4 partitions got sent to a single unifier before being output, right? And then I'll just go into just brief look at some of the operators that in Malhar that actually support dynamic scaling. So Kafka is one. So in this operator, what it does, it supports 2 strategies, one-to-one and one-to-many. So in one-to-one mode, what happens is for every partition for a topic on the Kafka side, an operator gets created on the Apex side. And each of these are parallelly reading from the different partitions. In the one-to-n case, multiple partitions on the Kafka side are assigned to a single partition on the Apex side. And how this gets distributed is actually controlled with throughput. So you can specify a maximum throughput. Till the maximum throughput is reached, each individual operator tries to greedily pick up as many partitions as possible. Once the throughput threshold is crossed, then essentially new operators get created on the Apex side, and the partitions get redistributed. Okay. So another example is the file reading operator. So what it does is, say you have a bunch of files in a folder. It basically you specify the number of the number of files you want each partition to read. Actually, you specify the number of you specify the number of partitions to start with. Then what it's going to do is it's going to allocate the files among those partitions based on the hash code of the file name. So in this case, for example, file 1 and file 5 could be going to one partition, file 2, file 6 could be read by other partition, and so on. So that's how they will redistribute, reading. That's how they will basically not trample on each other and basically read from different files. Now this works fine if all your files are similar sizes, right? But if one file is big and one file is small, one of the partition is going to get burdened, right? So in that case, you want a more egalitarian or a better work division approach. So in that case, you go with a block-based partitioning. So essentially, what happens is in HDFS, the files are divided into blocks, and each block is the same size, right? So what happens is we'll basically each partition then is just reading from different blocks, and one file could be read by multiple partitions, but they're just going to be reading from different blocks. And this particular block reader operator can dynamically scale up and down based on number of pending blocks or the number of pending files that have to be read, right? So you can specify a minimum and maximum. So if you say I want maximum of 16 partitions, so if there are 16 blocks available, it's going to create as many 16 partitions. They're all reading parallelly, and as soon as the number of blocks to be read is pending blocks goes down, it'll scale back down to 2 partitions. Okay. So let's try to understand how scaling now works in Apex, right? So first of all, the scaling itself is actually divided into 2 pieces, and user has total control over both the pieces. There is the when to scale, and then there is the how to scale. Okay. So what I mean by that is when do you decide to scale, right? So that's something that's exposed to the user as well, and it's an API. It's called stats listener. So a user can basically write a stats listener. By user, I mean the developer of the application, right? They can write a stats listener where they are continually given stats of your different operators, and they can make a decision based on that on when to scale. So suppose you see that your input is reading at, say, 100,000 events per second, and your downstream is only parsing at 50,000 events per second. That may be your decision to scale. Okay, I'm falling behind. Or you may have a fixed limit, right? Maybe you already pre-benchmarked your operator, and you know that your operator is going to perform well as long as the number of events is 20,000 events per second. Once it crosses, you want to scale. So essentially, your stats listener is given this information, and you can decide to scale, right? Now, when you scale, it's not just not as if more partitions are deployed and we are good to go, right? Because what's going to happen is when new partitions get deployed, some of the data that used to be going to old partitions now starts getting redirected to the new partitions, right? Now, you may have state or you may have memory that's in the old partitions that need to be actually part of the new partitions. So one example is, let's say you're doing key-based counts, right? And it's a cumulative count that you have kept in memory, like a word count, right? So earlier when you had two partitions, each partition, let's say for first partition was getting all the words that started from A till F or something, and the next one got from G to Z. Now, when you went from 2 to 4, some of the G to Zs will probably go to the new partition, right? So the old counts for those words needs to be present in that partition. Otherwise, you're going to get wrong results, right? So essentially, when this partitioning happens, it needs to be stateful. Your existing state may need to be moved from existing partitions to new partitions. Make sense? So Apex provides, the Apex scaling API gives you a way to do that. You can actually, depending on the business logic of your application, you can actually distribute the state when you're scaling. And when you do this, right, and the DAG kind of reconfigures to the new structure, all this is done without any loss of, dropping of any data, or it's all done in a very consistent fashion, right? So some of the scalars we provide out of the box, of course, is like you saw, if you remember for the parser, when I was specifying the number of partitions, I basically said stateless partition : 4. Because the reason is because scalar, you can basically, we don't assume that the static is the default, right? You can basically specify any scalar, and static is one kind of scalar. The fixed number of partitions is one kind of scalar. So that you get that, that's available. You can just use that. It's in Malhar. So you can specify the number of partitions. You also get a dynamic throughput-based scalar and a latency-based scalar. So essentially, you can say you can use a dynamic throughput scalar where you can specify an upper cap and a lower cap of the events per second. Once the upper cap threshold is breached, then your operators will get partitioned. And similarly, when the lower threshold is, if your processing rate goes below the lower threshold, partitions are combined, right? But these will work only when your operators are stateless, because they don't know about what state you carry in your operators. So if you have state, then you can extend these scalars, and then you can write your state transfer. Of course, you can write your own scalar. So if you want to do time based on time of day, like let's say you're expecting a lot of data at 10 a.m. and you want to scale at 9:30 a.m. and be ready for it, you can write your own scalar, right? So if you're writing a scalar, typically you would implement two interfaces, a stats listener and a partitioner. So stats listener is the one that's given the stats, and then it can look at the stats and make a decision to partition. So all it tells the engine is, okay, it's time to partition now, right? By stats, I mean not just the system level stats like throughput, latency that we provide. You can provide your own stats. So in your operator, you can have your own metrics. So for example, if you're writing a dedupe operator, and number of duplicates is a particular metric, you can use that. So you can provide your own custom stats from the operator to the stats listener, and you can use that to make your decision to partition. And when it's time to make the decision to partition, basically the define partition method will get called on your partitioner, and you're basically, it's a very simple interface. You're given the existing partitions, and you return the new partitions, right? So it's kind of like a intuitive, counterintuitive moment. So it's like basically what it's doing is it's giving you the last checkpointed state of all the partitions, and you are basically taking that and providing a new list. So you can say that I want to keep all my existing partitions, plus I'm going to add 2 more, right? And then this new thing will get redeployed. So essentially you can return existing partitions in the new collection, as well as add new partitions. And when the partitions that you return as is, they will not be redeployed, and the new ones will be deployed. Similarly, if you want to reduce the number of partitions, you can remove some of them from the list, and you can return a new list. So essentially, the ones that you removed will get undeployed, right? So it's a very simple interface that you can use to partition any way you like. And you can see some examples in that folder that I've indicated. And the last is, so now that you have all these partitions, how is the data actually split? And, how do you know which data goes to which partition? Right? So by default, what we do is, because the data can be any Java object, we take the hash code, And the way the default partitioning mechanism works is it takes the last few bits of the hash code and accordingly routes it to the different partitions. So if you have 4 partitions, it's going to look at the last 2 bits, and based on that, it's going to go to one other partition. But what you can do is you have a lot of control here. So essentially, if you don't want to look at the hash code, but you want to define your own hash code, you can implement a stream codec. And this interface lets you define your own hash code on the data. So for example, if you just want to use one key in your big object to be the key for partitioning, you can do that. And similarly, with stream codec, you can also control the serialization and deserialization. And this mask and the resultant partition where it goes to, that can also be controlled by the custom partition. So this define partition methods, when it returns, it not only returns the operators to deploy, but it also returns this map, right, of what you want. So one example is, let me show you this one. So let's say you want a piece of data that's emitted to go to all downstream partitions, right, like a broadcast. Then you can set the mask to 0, and you can say all the partitions will listen to 0. So what will happen is the hash code will basically be ANDed with the mask, and since it's anything ANDed with 0 is 0, and all the partitions are listening to the result 0, the data will go to all the partitions. So you have full control of how you can actually move this data around. Okay, so here are some resources on Apex and generally partitioning. And yeah, that's all I had. Any questions? Yes? So ordering within, ordering is not maintained when you actually go to multiple partitions and data is getting shuffled across, right? But within a stream, between 2 partitions, the data is ordered. Okay, so if you want data to be ordered between 2 different or multiple paths, then you have to implement something additional in the data itself. Yeah. Yeah, that's a good question. So they will run inside the app master as a single instance. Yes. Yes. Yes, the defined partitions will be called when you set it. Yes. Yeah.
So the goal of partitioning is try to improve scalability, right?
Trying to hit your SLA, right? Whatever is your...
Oh, SLA, okay.
Yes.
So in terms of, my question probably a little bit off topic. So in terms of language itself, like Python, it's not highly scalable because of concurrency issues, or there are lots of language built-in issues. Even Java is not because of JVM. So from language point of view, how do you kind of improve scalability as well as SLA,
Yeah, I mean, you can't go faster than, what you can do is you can maybe break your logic down into smaller operators and then, pipeline it that way. But once you hit that atomic unit, that will, how fast it can process the data would be the limiting factor. But essentially with partitioning, what you're doing is you're trying to create more instances of the same logic and fan the data out, right?
So it is, in terms of partitioning, how do you choose the right granularity?
So
the operator, right? You're talking about the partitioning, the functionality into operators, right?
Yes. So, I mean, most of the time as you're building the application, right, as you're trying and testing it out and so on, you can see, how an operator is performing. And once you have ironed out your initial programming issues and so on, right, then you pretty much know the limit of how much a particular operator can process, right? At which point of time, if you need to process more, scaling is your option, right? You create more instances, and then you choose whether you want to go static or dynamic.
So based on experience, domain knowledge, and also you are assuming the cluster is fixed, the topology is fixed. Are you assuming when you do partition, are you assuming the cluster is fixed? The topology of cluster.
In what sense? You mean the nodes, or?
I mean the cluster is running. Apex is running on top of cluster, right?
Yes.
So assuming it's fixed, the topology of cluster.
Well, what we do is, to actually get the resources, we use Yarn, right? So we're actually getting the resources from Yarn. So we just ask Yarn for giving us more resources. So if, for example, during dynamic partitioning, you ask for 4 more containers, then we ask Jan for 4 more containers.
Also, so the cluster can be scaled out.
Yeah.
Okay.
Yeah.
Control the hash code that got generated?
You can. If you implement the stream codec, then you basically can return a custom hash code. So it doesn't have to be the hash code method of the object. Yeah.